By properties of trapezoids and kites. There are three special types of quadrilaterals that we study other than parallelograms. And these are the trapezoid, the isosceles trapezoid, and the kite. Trapezoid, if we draw a picture of each of these, trapezoid is a quadrilateral with one pair of parallel sides. Okay, so something like that. We call those sides bases. And, oops, let's go ahead and connect those there. All right, the angles are attached to base angles. So base angle there, 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 and there. Okay, so 4 base angles. And the non-parallel sides we call legs. So this is a leg, and this over here is a leg. Okay, so the big deal here are that you have one set of parallel sides versus 2 set, which would be a parallelogram. An isosceles trapezoid is a special type of trapezoid where you have your trapezoid, so you have your parallel sides, but then your legs are also congruent. Okay, and since the legs are congruent, that would mean your base angles attached to a common base are congruent. Okay. All right. A quadrilateral that has 2 pair of consecutive congruent angle or congruent sides and opposite angles that are opposite sides that are not congruent is called a kite. So a kite, if you can just picture more of a kind of an old school kite there. A kite has adjacent sides that are congruent and opposite sides are not congruent. Okay, you have one set of adjacent angles or opposite angles congruent on the kite. All right, so that's what we've got. I try to clean up that drawing a bit. All right, so let's go ahead and take a look at this. Let's show that ABCD is a trapezoid. And then see if it's isosceles trapezoid. So the first thing we'd have to do is actually show that we have parallel sides. Would be one way to do that. Okay, the first way. So what I would do here is if I have a picture, I'd look at the slope, and that slope is pretty easy to find. It's a rise 5 or run 5, or a slope of 1. So the slope of AB, I'm going to write it like that. The slope of AB is equal to 1. I also want to find the slope of CD. In this case, can I rise 1 and run 1? And absolutely can. Slope of CD is also 1. Now, if it's already graphed for you, or if you graph it, then I just use rise and run on my graph to show the slope. Otherwise, if you're going to calculate slope using coordinates, remember to use the slope formula, y2 minus y1 over x2 minus x1. Okay, and so if you went that route to actually show this, and I'll just do it for, say, AB here, I'd have x1, y1, okay, and x2, y2. And so I'd have 5 minus 0 would be my denominator, and then 10 minus 5 would be my numerator. Okay, so I'd end up with 5 over 5, which we know is 1. Okay, so but if you already have a graph, then it's not worth doing that. The next thing I need to do is figure out length. Okay, and the reason is because I've shown it's a trapezoid. Well, you know what? I need to actually put a qualifying statement on there. Okay, same slope means line AB is parallel to CD. I guess we don't need the word line in there. Okay. Therefore, ABCD is a trapezoid. because one set of parallel sides. We obviously know the other two aren't parallel. Okay, if we look here, I'm going to find the length of BC. The length of BC is 5. It's a vertical length. A little harder to find that for AD. So to find the distance of AD, I'm going to write AD in subscript there. Distance of AD is going to be, remember your distance formula, it's x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Okay, so in this case, if I call this, since I've already got a x2, y2, I'm going to call this x1, y1 for the sake of what we're doing here. And so really I'm just finding the difference of my x's, so 5 minus 9, and squaring it. And then the difference of my y's, 10 minus 9, and squaring it. And I want to see if it's equal to 5, because if it's equal, then it's an isosceles trapezoid. So I have negative 4 squared plus 5, oops, not 5 squared, 1 squared. Okay, so root 16 plus 1, or root 17. And root 17 is not equal to 5. So ABCD is not an isosceles trapezoid. All right. So we have our two different answers there. Okay. Very good. All right. Let's go ahead and take a look at some other stuff here, some theorems that help us out here. Isosceles trapezoid base angles theorem. So you know that if a trapezoid is an isosceles trapezoid, then each pair of base angles is congruent. I already kind of pointed that out in our pictures. Whoops. Excuse me there. Let's switch that back. Okay, but we can mark that out. So if it's an isosceles trapezoid, meaning that, then we know the base angles are congruent, which that is congruent to that, that's congruent to that. Okay, next piece, let's go mark it up here. Isosceles trapezoid base angles converse just says the converse of the previous statement. So if a trapezoid has a pair of congruent base angles, then it's an isosceles trapezoid. All right. And so kind of taking a look at that, let's go ahead and first mark it up here. So we have our congruent base angles. And so based on those congruent base angles, no pun intended, I know that it's an isosceles trapezoid. So those are congruent, and there we go. All right, if an isosceles trapezoid, or the isosceles trapezoid diagonal theorem, a trapezoid is isosceles if and only if its diagonals are congruent. Now I kind of hope that you would pause this and try to take a look at it on your own, but that's what we have. It's isosceles if its diagonals are congruent, so that and that. So if we were to label this AB, CD, we would know that AB is congruent to CD. Or excuse me, AC, my apologies, that diagonal is congruent to BD. All right, so let's go ahead and apply those theorems here, using those properties here. Find the missing angle measures. Well, we have we have parallel lines, we have congruent legs, so therefore the base angles are congruent because it's isosceles. That's 70. And then remember, these are parallel lines. Therefore, these are consecutive interior angles or same side interior angles. Or in other words, you have parallel lines cut by a transversal. These two angles have to add up to 180. So 70 plus angle x is equal to 180. Therefore, measure of angle x is 110. And base angles are congruent. Therefore, angle W is also 110. Okay, there we got it. All right, and if Km is equal to 12, notice this is an isosceles trapezoid again. Congruent legs. Find the length of JL. So this is 12. And therefore JL is congruent because it's a diagonal, and diagonals of isosceles trapezoids are congruent. Therefore JL is also 12. Not terribly difficult, but just important to be able to apply those. All right, let's talk about midsegments and trapezoids. Midsegment of a trapezoid, it's a segment that connects two midpoints of the legs of a trapezoid. And the trapezoid midsegments theorem says a midsegment of a trapezoid is parallel to each of its bases. So if I have a midpoint and a midpoint, I'm just kind of estimating there. That line would be a midsegment. And that midsegment would be parallel to the basis. Now, if I can actually make my parallel line markings. And its length is, well, let's go ahead, let me show this. If I have this trapezoid and I kind of cut it out and then flip it over and then set it next to the other and piece them together, what I'd end up with is this trapezoid that really looks a lot like a rectangle. It would look a lot more like a rectangle if I could actually draw more of a straight line there, but there we go. And if I were to call this, say, base 1, that would make this down here also base 1. If I were to call this base 2, that would make this my base 2. And note that that base 1 and base 2, is equal to the same length as two midsegments, right? So from here to here, that gives me two midsegments. I'm just going to call them two mids, okay? And that's equal to base 1 plus base 2. So really, if I want to know what one midsegment would equal, I would have to divide both sides by 2. So if I divide this by 2 and divide this by 2, I end up with base 1 plus base 2 all over 2. Or more commonly written as midsegment is equal to 1/2 of the sum of my bases. Okay, so the midsegment of a trapezoid is parallel to each of the base, and its length is 1/2 the sum of the lengths of the bases. And that's how we get that there. Okay, so let's apply those. Switch that up. Using the midsegment of a trapezoid, find the length of AB. Well, notice AB is actually my midsegment. I know that because VA is congruent to VU, and WB is congruent to BX. You know, I should have really pointed that out here. This should be congruent to that. And these two are congruent as well. And remember, it's this side is congruent to this side because this is the midpoint. It's not this is congruent to that. Okay? This is congruent to this. This side is bisected by the midsegment. Okay, and so that's what we're shown here. In fact, we're showing it on both of these diagrams. This side FB is bisected by point T, the midsegment ST, because these two, FT is congruent to TB, and ES is congruent to SA. So the midsegment also bisects EA. The same thing applies here. So that means AB is a midsegment. Okay, and here ST is a midsegment. Okay, and so AB, if that's the midsegment, I know then AB is equal to 1/2 of the sum of VW plus UX, which means AB is equal to 1/2 of 9 plus 13. Or AB is equal to 9 and 13 is 22. Half of 22 is 11. So AB is 11. And similar over here, ST is equal to 1/2 of EF plus AB. So this time when we're trying to find AB, we already know ST. ST is 19. And that's 1/2 of, we know EF is 13 plus AB. So I'm going to get rid of this 1/2 by multiplying by 2. So that's going to give me 38 is equal to 13 plus AB. And then find that AB is equal to 38 minus 13, or 25. All right. Let's take another piece here. Identifying the midsegment in a coordinate plane. Hopefully you're getting really good at dealing with these now. If I'm trying to find the length of the midsegment, EF, in trapezoid, I can do it a couple ways. First, I can find the coordinates of EF by using the midpoint theorem of CD and AB, and then find the length of EF using coordinates. Or, since I know that EF is equal to 1/2 of CB plus AD, I could find the length of CD or CB and AD and cut it in half. And I think that's the route I'm going to go because I already know the coordinates for A, B, C, and D. So I'm going to find the distance of CB first. Okay? So the distance of CB, I have my distance formula. Just a quick reminder, distance is equal to x2 minus x1 squared plus y2 minus y1 squared. Okay, and so the distance, I'm just going to use my coordinates for C and B. All right, my x's, I have 10 minus 0 squared, and then my y's, oops, excuse me there, 11 minus 6 squared. All right, that's going to give me the square root of 100 plus 25, right, 10 squared and 5 squared, which is equal to the root of 125. All right, and I could actually call that, simplify that to root 25 times root 5, which is 5 root 5. Okay, so that's the distance of CB. Let's find the distance of AD. All right, and kind of the same idea here. AD, so I'm using my x's and my y's here in terms of x1, y1, and x2, y2. So I'm going to have 3 minus 7 squared plus 1 minus 3 squared is equal to negative 4 squared plus negative 2 squared. Now I'm hoping to kind of keep up here. You're pausing and trying this on your own. 16 plus 4, which is root 20, which is root 4 by root 5, or 2 root 5s. All right, so now I know AD and CB. I can substitute those in down here. CB was 5 root 5. Okay. AD is 2 root 5. So I have 1/2 of 5 root 5 plus 2 root 5s, or 5 of these root 5s and 2 of these root 5s gives me a grand total of 7 root 5s. Okay. And then 1/2 of 7 root 5s, or 1/2 of 7, is 7 halves, or 3.5 root 5. So the length of EF equals 7 halves root 5, or 3.5 root 5 if you want to evaluate 7 halves. There, we got it. Okay. Let's talk about one last thing, kites here. If a quadrilateral is a kite, then we already talked about one thing here, but let's talk about diagonals here. Quadrilateral is a kite, then its diagonals are actually perpendicular. All right, they cross at a right angle. And then the kite opposite angles theorem. If a quadrilateral is a kite, then only one pair of opposite angles are congruent. And I think I marked that originally. Okay, so once again, if we have a kite, then its opposite angles are congruent. And if we have a kite, then its diagonals bisect each other. Okay, so applying those two theorems, find the measure of angle B. Well, angle B is right here, and I know that angle B actually is congruent to angle C. And I know that all of these angles, because it's still a quadrilateral, ABCD, or the measure of angle A plus the measure of angle B plus the measure of angle C plus the measure of angle D has to add up to 360. And angle A is 90. And angle B is 50. And angle C that's not B, it's not 50. Sorry, D is 50. Angle C and angle B, they're congruent. And so rather than using two different letters, I'm going to say that angle B is X and angle C is X. I'm just going to call them both X. Because then I could just say that's X and that's X. And what that allows me to do, since I know they're congruent, I can use the same variable. And that now tells me that 90 and 50, or 140, plus X and X, or 2X, equals 360. And I subtract the 140 over, I get 2X is equal to 220. And I get 1x is equal to 110, which means the measure of angle B is 110 degrees, as well as C. However, they don't ask us for angle C. They're just concerned about angle B. So measure of angle B is equal to 110 degrees. All right, so if we were summarizing all of the properties of our quadrilaterals, all special quadrilaterals, parallelograms, rhombuses, rectangles, squares, isosceles, trapezoids, and kites. I'm going to go ahead and go through this, and I'm going to start with parallelogram. All sides congruent, and I'm thinking of every single parallelogram. So it's not always true. Opposite sides congruent, that definitely is true. Opposite sides are parallel, yes. Opposite angles congruent, yes. All right angles, not necessarily. Diagonals bisect each other, for sure, in every parallelogram. Diagonals are not always congruent. Diagonals are not always perpendicular. They do not bisect opposite angles every time. Base angles are not always congruent. One diagonal bisects opposite angles, no. One set of opposite angles are congruent, no. Okay, well, I'm going to move to rhombus. Well, first thing I know is a rhombus is a parallelogram, which means each thing that I selected for parallelogram, I have to also select for rhombus. But a rhombus also has other special pieces to them. Okay, a rhombus, all sides are congruent. A rhombus, well, not necessarily all right angles. Diagonals are congruent. No, not necessarily. Diagonals are perpendicular. Yes. Diagonals bisect opposite angles. Yes. Base angles, no. Nope. Okay, nothing else there. Okay. Well, let's go on to rectangle. Rectangle happens to be a parallelogram as well. So everything we had for parallelogram gets checked off for rectangle. Rectangle is not necessarily a rhombus. So let's check it out. All sides congruent. No, not necessarily. All right angles for sure. Diagonals are congruent. Yes. No. Yeah, oh, you know what? Base angles are congruent. That's for sure true there. Nope and nope. Okay. Well, let's move on. Let's go back to go to square here. Square is a parallelogram. Very good. A square is also a rhombus. And a square is also a rectangle. Holy cow. Only two things I haven't checked off for square here. Let's see. Only one diagonal bisects? No. Only one set of opposite angles congruent? No. All right. Well, we've got square. Square is the superhero there. Okay, let's go on to isosceles trapezoid. Definitely no on these. Opposite sides, no. No, not two sets. Diagonals are congruent. That's good. Diagonals perpendicular, no. Diagonals bisect opposite angles, no. Base angles congruent, yes. No. Okay. Not many there for isosceles trapezoid. Let's move on to kite. Kite, yowzers. Diagonals are perpendicular. Very good. Looks like those two there. So I've kind of summarized them all there. There's not a lot of crossover with isosceles trapezoids and kites and parallelograms. A little, you know, right in here and here. All right. That, I think, concludes all of our stuff about properties of special quadrilaterals. Okay, good lucky.